Okay, good morning, everybody. Good morning, everybody. Today is the last lecture for the semester, as you probably already know. And we are just gonna summarize everything that we have seen together this semester and draw some conclusion. And then at the very end, we'll talk a bit about the final exam and the final projects and the whole evaluation, how it works. So the main topics that we have discussed in this course are reactive control, optimal control, and reinforcement learning. And now we'll go over them one by one, starting from reactive control, of course. So reactive control, as we have discussed it here, was actually an optimization-based control approach, because we have also used optimization for doing reactive control. And in general, the goal of a reactive controller is to track a reference trajectory that can be specified either in joint space, in the easier case, or in task space. And that's a bit more challenging, but also more useful in practice. And here we have discussed inverse dynamics control, operational space control, task space inverse dynamics, also known as QP-based control, because we use quadratic programming as an optimization problem for finding the control inputs. And that was actually the main topic we have discussed. And there we have seen that we can include inequality constraints inside these optimization-based controllers. We can deal with underactuated systems, and we can deal with rigid contact constraints, which is especially useful if you're doing locomotion with legged robots. So the main advantages of this kind of control techniques is that they're extremely computationally efficient, because a QP problem is a very easy kind of optimization problem. It's convex. It allows for a direct solution if you don't have inequality constraints. If you have inequality constraints, there are iterative algorithms that are extremely efficient at finding a solution. And so you can find solutions in like 1 millisecond or even less. So these are very easy to integrate inside very fast feedback control loops, which allow you to get high performance on your robot. They are also flexible in terms of constraints, because you can account for velocity constraints like joint velocity limits, joint torque limits, also motor current limits, friction cone constraints. You can approximate them with linear pyramids instead of quadratic. Contact constraints, when you have rigid contacts, you can account for those constraints in your QP problem. And I would also say they're quite user-friendly, because they're not difficult to use. I mean, once you know the theory and you implement it either yourself or using a library like we did, it's not hard then to tune the hyperparameters, because the main hyperparameters you have are the weight of each task and the feedback gains of each task, but they're quite easy to tune in my experience. And so I would say these are user-friendly methods. The disadvantages are that we have discussed they can hardly account for position level constraints like joint angle limits or collision avoidance constraints. You can try to include them, but since it's an instantaneous control method that doesn't have a preview into the future, it's very hard to make it work. And you can very easily end up having an unfeasible optimization problem if you try to include these position level constraints. So they're not really meant to be used for that. And they need a reference trajectory. So maybe just having a reactive controller is not enough for what you want the robot to do. It depends really on the task. If it's a task where the reference trajectory is automatically inferred from the task specification, like you want the robot to like cut material with the with a knife or with a laser, then of course you know from the shape of the cut what is a trajectory that the end effector should perform. In that case, you can just do what you want with a reactive controller. But if your task specification is a bit more high level, like you want the robot to reach this point in minimum time or with minimum energy, or you want to reach a certain location while avoiding obstacles in the environment. In this case, there is not a single way to do this in terms of trajectory to track. You have multiple ways, and it's not obvious which one is best. And so in that case, reactive control alone is not enough. But for this, we can try to use optimal control. So in optimal control, as we have seen it, the goal was to compute an optimal trajectory while satisfying a set of constraints. Here we have seen that we can transform the optimal control problem into a numerical optimization problem by using different approaches, which were single shooting, where we only use the control inputs as decision variables, collocation, where we use both control inputs and state as decision variables, and multiple shooting, which was an in-between approach where we use all the control inputs and some states as decision variables. And then if you want to do also control in terms of like feedback control and stabilization, you can try to solve this trajectory optimization problem inside your feedback control loop, so at a high frequency. And you end up doing what is called model predictive control, or MPC for short, which comes with its own challenges of ensuring stability, ensuring recursive feasibility, and a more pragmatic one, ensuring that computation time is sufficiently small that you can do this in a fast feedback loop. Here we've also discussed some specific applications like obstacle avoidance, first with circular obstacles, then with polygonal obstacles. How to do minimum time trajectory optimization, where you want to minimize the time to do some things, typically to reach a target. And in the second assignment, you've also seen how to do path following. So you're given a path, but not a time law for how this path should be tracked. So this is a more like the generalization of the classic trajectory tracking problem. And you can figure out, you can let the solver figure out on its own what is the speed at which the path should be followed. So what are pros and cons of optimal control? It's a long list on both sides. So in terms of advantages, I would say the main one is that you can account for any kind of constraint. So acceleration, forces, velocities, positions, you can just put it in and it's going to work. So it's very flexible in terms of which kind of constraints you can include. And it's also very flexible in terms of what kind of metric you can optimize. You can do like minimum energy, minimum time, you can do path following, obstacle avoidance, anything that you can think of more or less. You can just formulate it. You can add extra auxiliary variable like we did when doing obstacle avoidance for avoiding polygonal obstacles. You remember we included extra variables in the problem to find these half planes to separate the robot from the obstacle. You can get creative and do a lot of stuff with this tool. It's computationally cheaper than RL because you can get these trajectories typically in a matter of seconds or even fractions of a second, depending on the system you're working with. So with respect to RL, which takes typically minutes or hours to train a policy, this is much faster. You can also do control with this, not only offline trajectory optimization to get a reference, but you can also re-optimize the trajectory online doing MPC. And I would also say this is relatively user-friendly because there are these optimization solvers off the shelf, like IPOpt, the one we have used, which don't require much tuning from our side. I mean, you can just use them with the default setting and they work. Then, of course, if you know your way around an optimization solver, you can tune it. For instance, we have played a bit with the maximum number of iterations when we wanted to do MPC to make it fast. We have played a bit with the convergence thresholds, but we haven't done anything beyond that. So I would say that it's relatively user-friendly. However, we also have a quite long list of disadvantages. For instance, we need to have differentiable dynamics, differentiable cost, differentiable constraints. Anything basically we put inside an optimization problem needs to be differentiable if we want to use gradient-based optimization, which is what we have been doing for the whole course, basically. And this is limiting in robotics application, especially because dynamics, when you have contacts, becomes non-differentiable. So that's kind of a big problem if you want to do robotics trajectory optimization and you have contacts, like intermittent constants that are made and broken during the motion of the robot. Also, I said that it's computationally cheaper than RL, but it's also computationally demanding to do MPC because you need to solve this optimization problem in typically 10 milliseconds or so, and that becomes challenging. So if you want to do just offline computation to get a reference, then trajectory optimization is super fast for that purpose. But if you want to do online stabilization of a robot, then the requirement in terms of computation time becomes much more challenging to meet. And at that point, trajectory optimization becomes MPC, and that is hard. So that requires some effort in terms of implementation to ensure that you meet the computation time requirements. There is a problem of local optima, which we have also seen. Sometimes the solver falls into very bad local optima, and you need to do something to help it get out, like provide an initial guess, which is non-trivial. It's not just all zeros. So that can be more or less of a problem depending on the specific application you're working with. We have seen with the unicycle, for instance, there were a few situations in which the solver ended up in local optima, but it was also relatively easy to get it out of it just by providing a decent initial guess. It needs state estimation. This is a topic we haven't discussed, but there are other courses where this is discussed at length. Probably you have taken some of them, or you will. We always taken for granted that we know the state of the robot. We know X. And that's what we use to do feedback control. In practice, for most robots, you don't know the state. You have some sensors. The sensors typically give you a part of the state. Like for instance, on a manipulator, you have encoders. Those give you the joint angles. You don't have a sensor measuring the joint velocities. So you need to estimate the joint velocities. And that's easy. But if you have a mobile robot, like a quadrator or a quadruped, an underwater robot, whatever robot moves around like a vehicle, you don't have a direct measurement of the position of the robots in the environment, in the world. And so you need to estimate that from sensor measurements. Like maybe you have LiDAR, a LiDAR sensor, or you have a stereo camera, or if you're in a laboratory, you might have a motion capture system, which makes life easier. And so you need to work on state estimation to figure out what is the position of the robot in the environment, starting from these measurements. Of course, this estimation is always going to be a bit delayed, a bit noisy, a bit biased, and that makes life harder for the controller. And with optimal control and trajectory optimization, you need to have that kind of estimate. Another thing, it's hard to account for uncertainties. So in optimal control, we have always assumed that we know exactly the robot model, we know exactly the robot state, we know everything, and then we can compute these locally optimal trajectories. But in practice, the robot models that we have is an approximation of the real dynamics of the system. And so it would be nice actually to compute a trajectory that is robust to the uncertainties that we have on the robot model. There are techniques to do that, like robust trajectory optimization or stochastic trajectory optimization / MPC, but those are much more challenging. So we haven't had the chance actually to discuss them. And typically, most of the work has been done for linear systems, and we know that robots are not linear in general. So there are also works on nonlinear systems, but they are much less grounded. They're more relying on approximations. So that's definitely a big challenge for trajectory optimization. Just a few extra words on the issue of contacts, because that's a big one in robotics. We have said before that when you have rigid contacts, the dynamics of the robot becomes non-differentiable, because from the moment where you're free and the moment where you're in contact, you have like a discrete switch in your dynamics. So you have extra constraints that are added, like a moment before touching. If you push down on your foot, the foot moves down, right? The moment you touch, if you push down on your foot, the foot doesn't move. You just get a force as a reaction of that pushing down. So at that moment where you make contact, there is a discrete switch in the dynamics, which makes it non-differentiable. And actually, it's also discontinuous, because your velocity goes from being non-zero to being zero in just an instant of time. So you have a jump in the velocity. So since this is a non-differentiable dynamics, gradient-based trajectory optimization cannot be used. So it would seem that we can do nothing basically as soon as we have contacts. Things are not that bad in practice. For instance, there is this solution, which is to say that you fix the contact sequence a priori. So you decide beforehand what is the contact sequence that the robot should go through during the motion. And if you do that, for instance, assume you have a biped robot and you want to compute a walking trajectory, well, you can easily guess that the contact sequence will be right foot, left foot, right foot, left foot, and so on forever. So you decide that sequence beforehand. And once you have done that, basically your dynamics is no longer non-differentiable. It just becomes time varying. Because depending on which foot is in contact, you have a different dynamics. But everything is differentiable at this point, because you already know what is the sequence of contacts. You don't have to guess. And you can still optimize where you're going to make contact and at which time you're going to make contact. The only thing you've given up is changing the order in which you're making contact, which is not so bad in certain, depending on the application, of course. In some applications, it's terrible because figuring out the order of the contacts is very hard. But in others, like bipedal locomotion, it's trivial. And so already with this trick, there are many problems in which you have contacts that you can tackle with trajectory optimization. There are also other approaches which try even to figure out automatically the order of the contacts, for instance, by making the contact model smooth instead of making it exactly rigid. They make it a bit compliant. That comes with other challenges, but that's also something that people have investigated and can be done. That makes everything less user-friendly. Okay, let's talk a bit about reinforcement learning. So in reinforcement learning, as we have seen it, the goal was always to compute an optimal policy, not an optimal trajectory like in optimal control. So the topics we have discussed were dynamic programming, where we've seen value iteration and policy iteration. Then we have discussed policy evaluation with Monte Carlo and temporal difference learning. Then we have seen tabular methods, especially SARSA and Q-learning. And then we have seen how to extend this tabular method to the case where the state was continuous, which is what we care about in robotics. And there we have seen deep Q network as an extension of Q-learning to the case of continuous state spaces, introducing function approximation techniques to represent the Q function. And finally, in the last lecture, we have discussed about policy gradient methods, which allows for continuous action space as well. Just an extra bit of information. We have seen that in deep Q networks, we could consider continuous state, but not continuous action. So I think a natural question would be, can we extend it to deal also with continuous actions? Because we haven't actually discussed about that. And I just wanted to give you a quick hint that yes, that can be done. It has been done actually in 2015, so already 10 years ago, by proposing these methods called deep deterministic policy gradient, which you can think of as an extension of deep Q network to the case where you have also continuous actions, which could not be done with deep Q network. And the way they do it is basically maintaining a scheme which is very similar to deep Q network, but introducing an extra neural network to encode the actor. So the control policy is now represented by an extra neural network, which takes as input the state, and it gives as output the control inputs to apply to the system. And the way they train this neural network is by minimizing minus the critic, so minus the Q function, which is like maximizing the Q function. This is in the setting where you want to maximize thing and not minimize. So it's a RL setting where you want to maximize a reward. If you're in the optimal control setting, then you just minimize the Q function, which is what we always did. And just by introducing this extra network, you basically have now also continuous action spaces. Also for this network, they have a copy which they update at a slower rate, which is a target actor. And here the reasoning is very similar to the target critic, which we have discussed was already in the deep Q network algorithm. Okay, pros and cons of reinforcement learning. Main pros is very, very general as a framework. So you can just put in whatever cost, whatever dynamics you want, and it should work, at least in theory. Then making it work in practice may be challenging, but it can handle non-differentiable cost and dynamics, which instead is much harder to deal with trajectory optimization. It's computationally cheaper than MPC once you have the policy. So computing the policy takes a lot of time, a lot of training. But once you have the policy and you want to deploy it on the robot, you don't have to worry about computation time anymore, because the policy is just a neural network, and that typically can be evaluated very fast. So compared to MPC, with MPC, you have no pre-computation before deploying, but during deployment, you have to do a lot of computation. So you can think of it as if you're trading the pre-computation for online computation when you move from MPC to reinforcement learning. In one case, you do a lot of computation before. In the other case, you do a lot of computation during the control. Another advantage is that it has good exploration capabilities. So it's typically able to get out of poor local minima, contrary to trajectory optimization. And also these two features are very important. You can train directly sensor feedback policies, which we have seen with DeepQ network. You don't need to go through state estimation, basically. You can directly get a policy which takes as inputs the sensor data, and gives you the control inputs. No need for state estimation. So you just removed a big problem from the whole pipeline. And we will discuss this in a moment. You can also get quite easily policies that are robust to uncertainties. On the disadvantages, well, it's much more computationally demanding to train these policies and to solve a trajectory optimization problem. Of course, all the training happens before you deploy the policy, so you don't have like the real-time requirements to meet, like in MPC. But still, here we are often talking about hours of computation, or even days, depending on the system you want to control, the task you want to optimize, and also the hardware you're using for doing all the computation. And by hardware here, I mean GPUs, because modern RL basically requires GPUs. It's very hard to train without a GPU, except for toy problems, of course. Another disadvantage with respect to MPC is that it's hard to account for constraints. There are extensions of RL algorithms to include constraints, but they're not as well developed as the ones without constraints. And even if you use one of those, they can hardly give you any guarantee. So typically when you have constraints, trajectory optimization is a much safer choice than reinforcement learning. And also I would say reinforcement learning is less user-friendly than trajectory optimization, because the algorithms have many more hyperparameters. And in my experience, it's more challenging to get them to work well. So just using them with the default settings very often doesn't give you a good result, and you need really to spend time tuning these hyperparameters, which is made more challenging by the fact that computation time is higher. And so like testing a set of values for your hyperparameters doesn't require a couple of seconds, but maybe it requires a couple of hours. And that makes the whole tuning process much more frustrating.
Yeah. I got a question to the slide before. You said that you basically introduce another neural network that takes the state and then gives the action.
Yeah.
Then is continuous.
Yeah.
Why do I even need that neural network? Because I mean, like, I'm taking my action, giving that then to another neural network. Kind of like, why can I not introduce that neural network into the other neural network? So,
you mean this one?
Yeah, for example, I don't know.
Like merge.
I'm taking my action that I get from my new neural network, and then I use that to do everything, don't I?
Are you asking why can't I merge these two networks?
Yeah.
You can, and that's often done. Okay. That's often done. You can have like a single network that outputs both the value and the control action. Yeah.
And that also gives me then which.
Yeah, you can merge the two. Typically, maybe the two have a common part, and then at a certain point they split, and the final part is different. The idea behind that is that there might be some features of the state space which are useful both for predicting the value and the control. And so you learn these features only once through the common part of the two networks. But then at the end part of the network is different because, of course, what you have to output is a different quantity.
But the upper neural network, it doesn't give me the policy, just takes my states and gives me an action.
Well, that's the definition of the policy. That's the policy.
It gives me, so I don't have any input anymore. It's just using the current state and then basically does everything by itself.
Well, the input of the policy is the state.
Yeah. So I need these as a measurement, and then it calculates or does some magic, gets them optimal.
Yeah, it's just a computation. Basically, it's a typically feed-forward computation.
Yeah.
You can have also recursion inside, but that's quite advanced. In most cases, it's just a feed-forward computation.
Mm-hmm. So,
okay, let's talk a bit about the uncertainty things for the robustness of reinforcement learning, because I said that one of the advantages of reinforcement learning is that you can easily get robust policies that account for uncertainties, but I haven't explained you how you can do that. But this is a very important aspect of RL. I think it's one of the key reasons of its success. And the problem we are talking about is often referred to in the literature as the sim to real gap, which refers to the fact that there is a gap between your simulator and your real robots. So what if your robot's model is not accurate? Well, of course, an option is always to do model identification. You can just collect data on the system and do good old model identification and get a better model. And that could be enough to solve the problem. But sometimes that's very hard because the real model of the robots maybe is very nonlinear, and so it's hard to identify it, or you have parts of the robot model which depends on things that you don't measure, like temperature, humidity. I'm thinking especially about friction. And so it may be hard to have an accurate model for certain hardwares. So in that case, what you can do is to try to learn a policy that is robust, which means that it performs quite well over a range of different robots. Of course, it's not going to be the highest performance policy. It's going to be a bit conservative, but it's going to be robust. And so it's going to allow you to control your robot with reasonably good performance, which very often is exactly what we want. We don't want to have the top performance that's physically possible to have. Maybe getting 90% of the top performance is already good enough for many applications. So that's the objective. How do we get there? Well, it's surprisingly simple to achieve that with reinforcement learning. The way they do it is using this technique, which is called domain randomization. They always have these fancy names in RL. What it means is that when you train the policy, instead of running your simulation always with the same robot model, you randomize some parameters of that robot model. So sometimes your robot is going to have a slightly longer link. Sometimes it's going to have a slightly heavier link. Sometimes the friction is going to be a bit higher, sometimes a bit smaller. And you can introduce variance basically in your robot model. You can introduce delays. You can introduce actuator bandwidth limitation. Whatever you think is happening in reality, you can introduce it with some variation in the simulation. So what's going to happen is that your critic is going to see different data coming from different robot models, and it's going to learn an average of the value. And also your policy is going to see different data coming from different robot model, and it's going to learn like an average of the optimal control policy for every model. And what you end up with in the end is a policy that is robust to the variations that you have introduced during training. So that changes very little to the math and also to the implementation of your RL algorithm. And it just gives you a robust policy. And this works extremely well in practice. Yeah.
This variability becomes a hyperparameter, how much is important, to choose the variability?
It's important, but I mean, as long as you introduce a good amount of it, it's gonna work. Of course, as all hyperparameters, too much is bad, too little is bad. You need to find a sweet spot. But in practice, it has not been very difficult to find this sweet spot. You just basically, you typically have an idea of what kind of uncertainty you have on your robot model, or you can take some data to figure out how much this uncertainty is to make it a bit more grounded. But that's typically not very difficult. Also, another trick that is very often used together with domain randomization is that instead of learning a policy that directly gives you the joint torques for controlling the robot, the policy gives you a reference joint angle for each joint. And then you compute the torque with a simple PD feedback control. And mathematically, that's complete equivalence, because clearly by changing U, I can achieve whatever value of tau I want. So if you give me a policy that computes this desired joint angle, I can directly map it to another policy that directly computes tau. But in practice, this actually makes the learning simpler, because your robot is already stabilized by this linear feedback controller, and it also makes it more robust to uncertainties in the model. So typically these two things together are what actually makes RL work very well for real robots. And achieving the same level of robustness with trajectory optimization is much more challenging. Another key reason of success of reinforcement learning, which I already mentioned, is the fact that you can directly train sensor feedback policies. So policies that directly take as inputs sensor data. That allows you to get rid of state estimation. And even here, the way you achieve that is surprisingly simple. We have already discussed about that when I explained to you DeepQ network. You just basically replace the state as input to the neural network with your sensor measurements or a history of past sensor measurements. So maybe you don't just give to the network the most recent sensor measurements, but also the last, I don't know, 5 sensor measurements. So that gives to the network a view into the past, which the network can use to figure out basically the state starting from these sensor measurements. How much you should go into the past, that's a hyperparameter. So that's a bit annoying probably to tune, but typically you don't need to go very far into the past for robotics application. Just a few steps is enough. And that's very useful, because this allows you to train policies that work directly from raw sensor data, even pixel. So you can have policies that takes as inputs like images and output motor commands. Doing the same with trajectory optimization is much more challenging. I mean, you cannot have that direct mapping. You need to go from sensor data to a state estimate, and then you go from the state estimate to the control commands. Here, there is no need for estimating the state. You go directly from the sensor data to the motor commands. That's extremely difficult. And typically when you do that, you also simulate sensor noise when you get this sensor measurement to feed to the network. You add some noise to them so that when you deploy this on the real robot, the policy is robust to that sensor noise because it has been trained with sensor noise in simulation. This idea is very similar to domain randomization, which we have just seen. Another trick, well, a set of tricks that has been used a lot is the one of breaking down the problem into a sequence of incrementally more and more difficult problems. So in some cases, it has been found that learning directly a policy, for instance, to make a robot perform locomotion was too hard. And so the way people have managed to achieve, for instance, these very impressive control policies for locomoting over very challenging terrain with a quadruped robot was to break down the problem into a simple version, and then a version that is slightly more difficult, and a version that is slightly more difficult than that. It's a bit similar to the concept of worm starting. You're giving to the solver already something that is relatively good, but not good enough, and the solver just needs to improve it a little bit. And there are mainly two ways in which that's been achieved. One is a teacher-student distillation technique. So what you do is that you can train first a teacher policy which has access to privileged information. That would be, in this case, the exact state of the system, which of course is not going to be available at deployment time because, as I said before, for mobile robots, we don't have access to the state. But you start training a policy which has access to state because that's easier. And so the algorithm can find such a policy. And then once you have the teacher policy that is trained, what you can do is that you can train another policy, which is called the student policy, which doesn't have access to the state. It has only access to sensor data. But you can make its life easier by saying that this policy should simply imitate what the teacher does. So it's basically no longer reinforcement learning, it's imitation learning or supervised learning, which is much easier. And so this policy here, then it's able to map directly from sensor data to motor commands. That's the teacher-student distillation. Another technique which is often used in combination with that is the so-called curriculum learning, from easy to hard. So you start by training the policy to solve an easy version of the problem you care about. And then once the performance are good on that easy version of the problem, you make the problem a bit harder until performance become good even on this second version. And you keep going until you reach the real problem you cared about. For instance, in locomotion, you may start to train your robot to walk on a flat terrain, and then you can make the terrain more and more challenging by introducing slopes, by introducing stairs, by introducing perturbation like pushes to the robot. And if you increase difficulty little by little, that has been shown to help the convergence of the algorithm. Of course, everything here introduces new extra hyperparameters, which makes the algorithm less user-friendly. But in practice, that's what made them work on really hard problems. And as a final note, I wanted to ask myself this question: is reinforcement learning really model-free? Because that's very often how it has been thought of and it is discussed. But I would say that for how things are going today, it's not really model-free. So in theory, reinforcement learning can learn a policy without knowing the model of the robots. But to do that, what you will need to do is to collect data directly on the hardware. And in practice, that's typically very challenging for two reasons. First one is safety, because you need to explore when you train the policy. We know it. And exploring on hardware can lead to catastrophic results, like the robots breaking, burning a motor, damaging the environment, or human beings around the robot. But most of the times, breaking the robot itself, because you can easily put the robots in a cage without any human. So human harm is not an issue there. But breaking the robot is an issue. And so safety is a big reason why it's very hard to do RL directly on the hardware. Even if we solved the safety issue, there is still the problem of how much time or how much money does it cost me to collect data on the hardware. Because typically these algorithms are quite data hungry. They require millions, if not billions, of samples, and collecting them on a real robot may take too much time. Maybe it takes weeks of data collection, and we don't feel like spending weeks doing the data collection on the robots. Of course, you could make time smaller by parallelizing. So instead of collecting data on one robot, you buy 10 robots and you collect data on 10 robots. Of course, it takes 10 times less. But then at that point, cost becomes an issue because you need to buy 10 robots. So you pay 10 times more for buying the hardware, which is typically not super cheap. So the solution was, of course, to switch to doing all this training in simulation, where safety is not an issue because robots don't break in simulation. And also time becomes much easier to tackle because you can parallelize on GPU. And simulation nowadays is typically faster than real time, unless you're working on a really super complex problem. But for most robotics problems, the simulator is going to be faster than real time. And so just by that, you can speed up the data collection. Then, of course, what is the limitation is that, well, if we need a simulator to train the policy, well, we need a model of the robot for the simulation. And if we accept that that is the main way in which we're going to use RL, then we can no longer claim that RL is model-free. It's model-based because we need a simulator. It's, however, derivative-free because we don't need the derivatives of the model. So that's, I would say, is the main difference that we have between RL with simulation training and trajectory optimization. So they both require a model of the system, but with trajectory optimization, the model needs to be differentiable and you need to compute the derivatives. With RL, you don't care. Okay, so you can be non-differentiable and derivatives are not needed. Just to clarify what is what. So if RL in practice is model-based, are there any model-free approaches in the literature? Yeah, there are, but at the moment, the main model-free approach is imitation learning. So imitation learning, we haven't discussed at all imitation learning in this course, but just to mention it so that you know it exists, it boils down to saying, I will just imitate some examples that I collected from an expert. The expert is typically going to be a human being, and the way the expert demonstrates how a task should be solved by a robot is through teleoperation. So a human being teleoperates a robot, so it commands a robot remotely, typically by a joystick or by a haptic interface, so that it can control the motion of the robot and it can show how the robot should perform a given task. You collect several examples of how the human teleoperates the robot, and then you train a policy to imitate these examples. And if you do that, Of course, you have solved the safety problem because there is a human in the loop. So the human takes care of safety. And you don't need many examples because you don't need actually to explore every possible action. The human is already showing you what actions the robot should perform to carry out the task. So you also solve the exploration issue. And you can with real hardware data without requiring any simulation. And so you really don't need a model if you go for imitation learning. Of course, here the limitation is that you need a human, you need to collect these demonstrations, and you can only do it for tasks that the human know how to perform and can teleoperate the robot for. Like for instance, locomotion is quite hard to do with teleoperation directly. Imagine a human teleoperating a robot that has to locomote. Since the dynamics of the human and the robot are different, the way the human walk is not necessarily feasible for the robot. So in that case, it's very much more challenging. But for manipulation tasks, actually imitation learning is working great. And here we can actually go take a look at some of these results. This is a paper where they use diffusion policies, which is this technique for doing imitation learning. And you can see here some examples of some manipulation tasks that they were able to train a policy for. Like this one here is called the push T task, the one on the right, where the robot has to push this T object on the plane to reach a certain configuration. You have the mag flipping task on the left, where the robot has always to put the mag upside down on the table with a specific orientation. And then you have the sauce pouring and spreading in the middle. The robot has to collect the sauce, put it on top of that sort of pizza, and then spread it out. So of course, you can imagine, especially this last task, it will be very difficult to have a simulator to simulate how the sauce moves as you touch it with the spoon. But doing that in the real world is extremely simple. And typically these actually are trained directly to predict motor commands from images. So you can have, again, image feedback sensor policies, which are very hard to achieve with other techniques. Okay, so that concludes the summary of the topics we have seen. Let's now try to compare a bit trajectory optimization and reinforcement learning, which actually we have already done quite a lot, but let's do it a bit more. So what's the difference between trajectory optimization and reinforcement learning? I think maybe before taking this class, you thought that trajectory optimization was a model-based approach, reinforcement learning was a model-free approach. I hope I have convinced you that's not really the case in practice. If I have to classify trajectory optimization and RL, I would do it in this table. So they differ for actually two things, which is what is optimized. So trajectory optimization optimizes a trajectory. Reinforcement learning optimizes a policy. And they differ for how they optimize it. So trajectory optimization uses derivatives. Reinforcement learning doesn't. So RL is derivative-free policy optimization. Trajectory optimization is derivative-based trajectory optimization. And at this point, you should wonder, okay, but what's here and what's here? Well, here you would have derivative-free trajectory optimization, which is actually something that's becoming quite popular in recent years. So what you end up doing if you try to do this is basically sampling-based optimization. So instead of using gradient methods like Newton's methods, gradient descent for solving your trajectory optimization problem, you can just collect random samples, evaluate the trajectory that you get through these random samples, and figure out a sort of like optimal trajectory starting from these random samples. And if you couple that with efficient implementations on GPUs, it turns out it can work. And the main advantage of these methods is that now you can tackle discontinuous dynamics because you no longer need gradients. And so here you have model predictive control methods implemented on GPUs that relies on random sampling and that can be used for contact-rich tasks such as locomotion and manipulation, where classic derivative-based trajectory optimization really struggles. If instead you look at what happens here you're doing policy optimization, but trying to exploit derivatives. So that is called model-based policy optimization. It's not as successful as this one, but there are some people who have tried to do that. I'm also working in this area, by the way. So the idea is, okay, I want to do reinforcement learning, but since I have derivatives of my robot model that I can use, I want to exploit them to make the policy training faster, more efficient, and so on. So if you have to compare reinforcement learning and trajectory optimization, which one is better? Of course, the answer is it depends. I would say reinforcement learning nowadays can tackle harder problems. You can deal with contact. You can have sensor feedback, direct sensor feedback without state estimation. And you can have uncertainties that are treated during the policy training. These things are very hard to achieve with trajectory optimization. However, if you have an accurate differentiable dynamic model for your system, or if your application is safety critical, so you really care about satisfying constraints to avoid really catastrophic outcomes, or if you need high accuracy, or if you need explainability of your control method, then in all these situations, I would still say that trajectory optimization is recommended over reinforcement learning because RL really struggles in these situations. And of course, as I was mentioning, in some cases, you don't need to choose, you can actually try to mix them. A big driver actually of mixing together techniques from reinforcement learning and trajectory optimization is safety, because safety is a very important requirement in robotics, especially when you have robots working alongside human beings. And reinforcement learning struggles with safety guarantees because typically you don't have constraints in the problem formulation. So it's very hard to make sure that the policy after training will never collide with the human being that's working close to the robot. So for safety, it's actually the area where we see most interaction between techniques from trajectory optimization, which can guarantee constraint satisfaction, and techniques from reinforcement learning. Okay, are you tired? Do you want to have a break? Okay, let's say yes. So let's take 10 minutes and then we discuss about the exam and the final projects after the break. So I'll see you back here at 42. Let's talk about the exam. So this is the same slide I've shown you the very first day of the semester. It summarizes how you are evaluated overall. There is a part of the evaluation which concerns basically writing code. So that includes the two homeworks, which you have already done. Those were optional, so in case you didn't do them, that's not an issue. Each homework counts for 3 points out of 30. By the way, today we should publish the results for the second assignment. Elisa is working on them. And before taking the oral exam, you will also have to hand in a final project. That counts for 7 points. Yeah. Okay, you're right. Probably I have to redo the sharing. Okay. So 2 homeworks, 3 points each. Final project that's bigger, so that amounts for 7 points. The deadline for the final projects is going to be a few days before the oral exam. At most 1 week, but in practice I always set it a bit later, like maybe 3-4 days before the final exam. I don't have a fixed rule because it depends how many of you are taking the exam on that day, because of course the higher the number of students, the more time I need to evaluate all the projects. So if it's more students taking the exam on that day, I need to set the deadline a bit earlier. Then the oral exam will consist in first discussion of the project. So basically before the exam, I evaluate your project and I will typically write down a list of questions to ask you about things that I don't understand about the project, or flows, errors that you've made in the project. I'm going to ask you questions to see if you're able to find the errors yourself with a bit of hints from my side. So that part, the project discussion, will contribute to 6 points. And then there's going to be 2 general questions about any topics that we have seen during the semester. And those are 6 points each. So if you do the math of all the points, you get 31, which is a bit more than 30, just to give you some room for errors. In case you didn't do both homeworks, or you're not satisfied with the mark you got on the homeworks, you can have an extra question to replace the mark for the homeworks. Yeah.
How long does the exam usually take?
How long?
Yeah,
it's 45 minutes each.
Per student.
Per student.
But isn't that, or yeah, is that kind of talking all the time, or like, yeah, I'm for 5 minutes?
Yeah.
It's just.
It's typically 15 minutes for the project discussion, and then 15 minutes for each question. If it goes very well, it can be faster. It can be just half an hour. If it goes bad, it can be longer. I typically don't deviate too much from the 45 minutes. I'm quite strict. But sometimes to help you, I may go a bit longer to give you more chances to say something valuable.
And are we giving the points right away?
Yeah. At the end of the exam, I give you the mark.
Good question. The homework, the assignments that we handed in, like we got points out of 30.
Yeah, you have to scale them to 3 basically.
But if I got whatever, like 9 points, do I get 3 or do I get?
You get 2.9.
Okay, so it's actually scaled.
It's scaled, yeah, it's scaled, and then at the end I do rounding, usual rounding. Okay. So 0.5 and above, it's rounded above, and below it's rounded below. Another thing to remind you, I already told you, but it's good to remind you. most of you are working in groups of 2 people. So a bit of an issue is when people from the same group take the exam on different dates, because you know they're going to have an exam date in January, another in February, and then one in June, one in July, and one in September. And you can take it whenever you want, how many times you want, hopefully only once, but some people have taken it twice because they liked it so much. And so if you're not coordinated with your teammate and you want to take the exam on 2 different dates, you can do it. It's not a problem, but it comes with a bit of a disadvantage for the person going second. Because if I discuss the project with your teammate who comes first, then I reveal basically all the errors, all the problems that I found in the project to the first teammate. And of course, I cannot then re-ask the same question to the other person. If you're coming on the same day, I will do the exam for you just one after the other so that you cannot communicate. But of course, if you come on different dates, for me, it's impossible to ensure that there is no communication between you. And so what I do is that the person who comes second skips the project discussion and just do an extra question. And that is a bit of a disadvantage, of course, because typically the project discussion is easier than just getting a question on any topic.
Regarding the question, is it more understanding and explanation, or is it like actual calculation stuff? Like, do you want?
I'm gonna go over that in a moment. It's only one day unless there's so many of you that I can't fit you in one day. So if you're less than up to 10 people, I will do everybody the same day. If it's more than 10 people, then I will probably distribute you over 2 days. So it's going to be the day of the exam and the next day. And if you have some constraint for the day of the exam, like maybe you cannot be there in the afternoon or you cannot be there in the morning, you can send me an email, and when preparing the schedule for the day, I can try to accommodate that. Okay, so basically this is just a suggestion. If you can come on the same day for the exam, I think it's good for you. Of course, it's not the end of the world if you come on different days. Many people have done it in the past, and many of them went very well, but it's just a bit harder maybe. Then, so that's the end of the slides, but to answer your question, what to expect at the exam for the 2 questions. Very often the 2 questions are just the title of one lecture. So, I don't know, I ask you, talk to me about MPC. And maybe that's it. And then you just go from there. And then depending on where you go, I might ask like more specific question. Like, okay, let's talk about the problem of recursive feasibility of MPC, or let's talk about the stability of MPC. But very often my starting question is very high level. It's a topic we have discussed for 2 hours at least. And that should help you, because instead of asking something very specific that maybe you have missed, I'm asking about a very large topic which you shouldn't have missed completely. Maybe you don't know some details about how to ensure the stability of MPC, but you should at least know what MPC is. You should be able to write down the mathematical formulation of the problem. That's very important. Please, at least the problem formulation of every topic, you should know how to talk about it and how to write down the math. So the optimization problem, like minimize, what are the decision variables, what is the cost function, what are the constraints, and try to be precise in that part, because that's important. Don't forget indexes, don't forget pieces here and there. You should write it down basically as I wrote it down in the slides. I'm not happy when I see things done halfway, especially with the math. Okay, so what happens sometimes is that there are people that are very good at talking about a subject, but when I ask them to write down exactly the math of what they've discussed, even if what they've discussed is completely 100% accurate, they cannot write it in math. Okay, there seems to be like a disconnection there. That's an issue. Okay, you should be able to write down the math. I don't care about knowing the details of the little things, but the math for the problem definition. So in general, I think a good rule of thumb is that the very few slides of every lesson are the most important ones for preparing to the oral exam. So make sure you know the first few slides of every lesson, because that typically is going to be the starting point for every question I'm going to ask you at the exam.
We have like 5 minutes after the question to write down some like the important equation that we have to.
No, we do it at the blackboard.
So we start directly from.
So yeah, typically you become the professor, I become the student, we switch, and I give you a topic, like, I don't know, dynamic programming or MPC or model-free policy evaluation. Can be any topic, and you start talking about that topic. So the ideal student would basically be able to kind of repeat the whole lecture I gave you on a blackboard, which is challenging, of course, because you have to remember a lot of stuff. But I never let you repeat the whole lecture, because I mean, I typically allocate like 15 minutes to one question. So typically I just see if you're able to give me the high level definition of what is the problem that we need to solve, how it is mathematically written down. And then I typically direct you towards some aspect of that lecture. And yeah, that's it. So in general, people who did their study in Italy don't have any trouble with your oral exam, because you are used to taking oral exams, so you know how that typically goes. People coming from abroad sometimes have had troubles. So that's why I've introduced this discussion here. I mean, not all people coming from abroad, but like statistically, as a percentage, that's coming more often from people that did not do their studies in Italy, because they don't know what to expect from an oral exam. So even if you're well prepared, you're not well prepared for this kind of exam sometimes. But I think that like telling you today what you should expect should fix that for most of you, at least. And I mean, if you have any doubt during your preparation, feel free to send me an email. I'm available to give you more detail. You had a question?
Will it be possible to have analysis of points from one of the questions, for example? Will you be able to get 4 out of 6 points from one question?
Yeah, sure.
Yeah.
Sure. I mean, that's most of the time what happens. You don't get the full score. You get something in between. So yeah, basically each question is graded, and then I actually do the grading from 1 to 30, because that's how I think typically. For each question, you get a mark from 1 to 30, and then there is an automatic averaging with weights that computes the final mark. And at the end of the exam, I tell you the mark, and you have to tell me within the day if you accept it or not. Okay. I mean, most people accept it, of course. Also because typically if you pass, the mark is typically quite good. It's very rare that you pass with a mark that's below 25.
What do you mean by accept? Do you mean like complain that you want a better grade, or do you mean like I'm going to take a new exam?
You cannot complain that you want a better grade. Some students have tried, did not go well for them. No, you should not complain about the grades. I mean, you can, of course, so you're right, but usually it's not a good strategy. But you can decline the mark and come later. Like if you take it in January, you can come in February, or you can come in June. Of course, second time that you come, we cannot repeat the project discussion. So the same rule applies that I discussed before. So you get 3 questions instead of 2 plus project discussion. But the good news is that the marks for the coding part, you keep them forever. So those remain even if you take the exam a second or a third time. Yeah.
Is it correct that it is 68%? That is the limit for passing and failing?
The limit is 18 out of 30, which is 60%. Yeah.
And this is then if you get 61%, is that like the lowest grade?
Yeah, 18 is the lowest grade, which you can accept, because below 18 it's not passed. But I mean, since a lot of the weight of the final mark comes from the homeworks and the final project, where you typically have good grades, even if the 2 questions maybe you don't perform super well, at the end when you do the averaging, it's very rare that you get a low grade. So I would say the vast majority is above 24, 25. And if you fail, then, I mean, when I say that you fail, very often is because you really did not answer anything to both questions. That's the most common case of failure. I ask you 2 questions and you just are not able to say anything about both topics. That's a fail. Even if the average of everything else would be sufficient, that's still a fail. Okay. So you need to answer like decently at least one of the 2 questions. Yeah.
Regarding the 2 questions, we don't have like some preparation time. Like we enter the class and you give us the 2 questions and we can write something on a piece of paper.
No, you don't write anything. You just talk at the blackboard, and you can use the blackboard for writing the math. But you're gonna just write math on the blackboard. Everything else you just say to me, because it's gonna be, it's a discussion, discussion between the 2 of us. There's gonna be Elisa also in the room, the teaching assistant. She's just there to testify that everything is going according to the rules and I am not abusing you verbally, this kind of stuff. But the discussion is gonna be between you and me. Okay. Well, if you have any other question on the exam later on, just write me an email. And let's now discuss a bit about the final project. So for the final project, I'm actually giving you 3 options, so you can choose the one that you prefer. They are all quite similar in terms of difficulty, so there shouldn't be an easier one. You can just choose according to your taste, what is that you're more interested in. The first project is learning a value function with a neural network and using it as a terminal cost in an optimal control problem. The second one is learning the viability kernel of a system and using it as a terminal constraint in an MPC framework to ensure recursive feasibility. And the last one is learning a value function, then learning a policy by minimizing the corresponding Q function, and finally using this policy to warm start an optimal control solver. So in all 3 projects, you have to learn something with a neural network. So that's the common part. And you will also have to solve trajectory optimization problems. So in terms of the technical challenges, they're quite similar. Okay. Well, the submission procedure is the same as usual. And here in this document that I will share with you in the afternoon, you can find a description of the software tools that you will need to use. For solving optimal control problems, we're going to rely on Casati. That's my suggestion. I mean, we have used it throughout the course, so you should already be familiar with that. For the neural networks, you can use whatever library that you want. You can use PyTorch, you can use TensorFlow with Keras, you can use JAX with Flax. But last time that we did the tutorial on neural networks, what I've shown you is PyTorch, and my suggestion is to stick with PyTorch. Also because there is this library called L4Casati, which allows you to very easily integrate a PyTorch neural network inside Casati. And that's very useful, especially for the projects A and B, where you need to do this integration of the neural network inside the optimal control problem. So that makes your life easier. So unless you're already a guru in TensorFlow and you know nothing about PyTorch and you're not willing to learn it, in that case, okay, you can stick with TensorFlow. But for most other people, I would say use PyTorch. Another thing that can be very useful for these projects is exploiting parallel computation. I think all your laptops have multiple cores on their CPUs. So you can exploit multiple cores for doing computation faster. There is this library called multiprocessing in Python, which helps you parallelizing your computation on a single script. So I suggest you to use that when you need to, for instance, solve many optimal control problem. You can do that in parallel and make that maybe 5 times or 10 times faster. So that's going to make your life much, much easier. And then what follows are details about every single project. Just a general rule of thumb, the last project, project C, is the one that has more of a reinforcement learning flavor, because you're doing actually policy training using a neural network to train a policy based on Q function. So if you want to explore more the RL side of things, I would suggest taking project C. Project A and project B instead are more like MPC based projects, even though they include a neural network and a learning part. But what you end up doing in the end is MPC basically. So that's a way to choose. Actually, I would have loved to give you also a project that was really pure RL. But the fact is that RL is much more challenging in terms of computation requirements. And I didn't want to give you a type problem which you could have solved easily with trajectory optimization to do with RL, because that would seem too artificial to me. And so I didn't find a good trade-off between something that is too computationally challenging, that you would require a GPU to work with, and I cannot assume you have a powerful GPU to work with, and something that would be like a silly type problem. And so I decided not to give you any pure RL project. But if you do think you can work on a pure RL project because you know your way around it, or you're willing to take a risk, you can contact me and we can set up a project specifically for you that's more RL based. Like, for instance, if you want to work on a PPO implementation for something like the push T task, which we have seen before, or you have this T object on the plane and you need to push it. If you're willing to take the risk, because it may be more challenging than these projects here, you can contact me and we can define the details of that project. Okay, so going through every of these projects would take quite a long time, but I don't think it's strictly needed because the projects are described in a quite detailed way already in the PDF. So I think you should take your time, read carefully the PDF to choose the project. And also, I mean, read it very carefully once you've chosen the project, because very often the mistakes that people have made in the past were because they didn't read carefully the instructions. So something was written clearly in the instruction and they missed it and they did something different which did not comply with the requirements. Okay, so I know maybe it's a bit boring, but take your time and read carefully what's written in this PDF, because this is basically the metrics by which you will be judged for the final project. So take your time. Maybe we can just go over the very first project, which gives you a bit of an idea of how all projects are. So in the first project, you need to, first of all, start by solving a sequence of optimal control problems, which all looks the same, except for the initial state. And that allows you to compute what is the optimal cost associated to each potential initial state. And then once you have this data set of data where you associate to each initial state the corresponding optimal cost, you can use this data set to train a neural network. So you're going to do supervised learning to learn how to map the optimal cost to the initial state. And that is basically what a value function does. So the network that you're learning is a network that you can use as a value function. And that's exactly what you need to do later. So the network is going to be called J, and you can use this network as a terminal cost in an MPC formulation, because that's an approximation of a value function. And what that should allow you is to use a very short horizon in your MPC formulation, because you have the value function that basically compensates for the rest of the horizon that is missing. Of course, it's not infinite horizon. It is an horizon of length n, which is the one that you use for generating the data set. But basically, you're solving an MPC with an horizon m, but it should give you a solution that is comparable to that you would get with an horizon n plus m. And that's exactly how you should evaluate the performance of the whole system. You're then going to compare the performance that you get using an MPC with an horizon m, which is going to be short, and an horizon m with the neural network as a terminal cost, which should be much better. and an horizon n plus m without the terminal cost. We should be very close to what you get with the terminal cost and the shorter horizon. Things are going to be quite similar for project B, but in project B, instead of learning a terminal cost, what you need to learn is a terminal constraint. But the idea is very similar. So project A and project B are quite symmetric. Project C is a bit different. As I told you, it's a bit more RL in flavor, because after you learn the value function in a way that's very similar to project A, well, it's not very similar, it's exactly the same as in project A, then you use the value function to train a policy. So you're gonna optimize the parameter of a neural network, that is your policy network, to minimize the Q function. So this is basically the optimization problems that you're gonna be solving. This is exactly the same that happens in the DDPG algorithm that I presented you earlier, which is how you do continuous action policies starting from DQN and extending it. Basically, the extra step that is introduced in that algorithm is exactly this step here that I'm asking you to do. So it's a policy optimization step. And so you, at the end of this, what you get is actually a neural network policy that you can directly use to control the system without solving trajectory optimization problem to do MPC. So in this regard, it's more similar to RL because you do policy optimization. Okay, at the end, you can find a list of suggestions for preparing the final report, because what you will need to end in at the end, as for the assignments, is the code in a zip file and a PDF containing a description of the work and the results. And here's everything that basically you should include in the report. So make sure to read the list and follow the list. And as usual, if you have any doubt on the final project description, just send me an email, and I will answer pretty fast, even during the holidays, I promise. That's it. Yeah.
Do we have a number of pages that we?
There is no limit. As usual, my suggestion is don't go too long. Some people have gone quite long, but of course it depends why you go long, because maybe you have many plots. That's acceptable as long as they are useful. Don't go too long with the text. Especially, there is no need to summarize the theory of the tool that you're using. Some people like do a summary of the lecture on trajectory optimization, which, okay, I mean, you can do it, but I'm just gonna skip it. I'm not gonna read it. So I already know the topic pretty well. It's not, and it's not required. I mean, what I want you to describe is really what you did, not the theory that I already explained to you in class. You just need to state the problem. So basically reporting this kind of equations here in your report to define the problem you're tackling. Yes, maybe even with more details than what I did here in this PDF. That's more than welcome, but you don't need to explain the theory. So typically people, if you're using a double column format, 6 pages are enough. If you're in a single column format, maybe 10. But I don't judge you by the length of the report. I judge you by the quality of the work, the quality of the results, the depth of the discussion. A lot of what you will need to do is parameter tuning. So make sure to discuss how you tune the parameter, what was the logic that you used. If you didn't get good results, but you explained well what you did and the logic of what you did, and it makes sense, you're gonna get a good grade regardless of the bad results. If you get bad results and you don't explain how you did things, you're gonna get a bad grade. So like explaining the logic of all the process, not just these are the final values of the parameters, period. Maybe that's acceptable if the results are great, but if the results are not great, it's very good that you explain how you got to those values, because at least I can judge your reasoning.
For the submission, we have just to upload on the platform.
It's gonna be like for the assignments, I'm gonna open a homework on Classroom, maybe 10 days before the final exam. And that's gonna have a specific deadline, which is gonna be a few days before the exam. And you will need to submit by that date. Yeah.
For the project discussion during the exam, we are going to both discuss the report and the code. Like the question are on both.
They can be on both. Most of the times we don't need to go to the code unless there was a mistake in the code that I spot, like an important mistake. And in that case, I may show you the code to show you the mistake. But most of the times the discussion remains on the report. And of course, since you're working in a group, it's acceptable that you somehow split the work in two, and you take care of one part and the other person takes care of the other. That's totally okay for me. But you need to know also the part that the other person did. So it's okay that you didn't do it, but you need to know exactly what the other person did, and you need to be able to discuss also the other person. You cannot say, oh no, this part I didn't do it, you should ask the other guy. No, that doesn't work. You need to answer a question on the whole project, not just the part that you did. Also, you're allowed to talk to each other about the projects, especially if you're doing the same project as another group and you encounter some issue and you want to discuss these issues with other guys, other students. That's okay for me. The one thing you cannot do is copy paste code. Okay. And people in the past have done it and didn't go very well for them, especially because I figured out later after the exam, and I had to go back and revoke basically the mark on the exam, and they had to repeat the exam several times with several also restrictions applied. So don't copy. Doesn't make much sense. Okay. That's it from my side. We have concluded the course. Thank you for being here the whole semester until the very end lecture. You're the few who survived. I hope to see all of you in January and February for the exam. And well, good luck with the studying.